You know, we've gotten incredibly good at understanding the cosmos. Our models are precise, they're elegant, until they're not. Today, we're diving into the glitches, the most fascinating planetary anomalies that just refuse to play by our rules.
All right, let's just think about this for a second. We are seriously good at space. I mean, we can fling a probe from our little blue marble, send it soaring across billions of kilometers of empty space, and land it within meters of where we want it to go. We have a handle on gravity, on orbital mechanics. It's a kind of precision that's just mind-boggling. Our models work. And for the most part, the universe behaves exactly like we predict.
But then, every once in a while, the universe throws us a curveball. A measurement comes back from a probe that's just a little off. An image shows a shape that has no business being there. An orbit starts to change when all our math says it should be rock solid. Something just doesn't fit. So, when we talk about a planetary anomaly, what are we really saying? And this is super important. This isn't some blurry photo or a one-time glitch in the data. A real anomaly, a scientific one, has to be two things. First, it's persistent. It doesn't just go away. And second, it's reproducible. We can point our telescopes at it again and again, and it's still there. It's a stubborn fact that just refuses to line up with what we think we know. And these stubborn facts tend to show up in a few different flavors. You've got your structural ones, we're talking bizarre, impossible-looking shapes. Then there are dynamical anomalies, where the actual movement of a planet, its orbit, does something totally unexpected. And finally, you have measurement anomalies. These are the sneakiest, just tiny, nagging little differences in the numbers that whisper, hey, you haven't quite figured this out yet. All right, let's open up our first case file. This is a structural anomaly that is just as beautiful as it is baffling. We're heading out to the gas giant, Saturn. So picture this. It's 1980. The Voyager 1 spacecraft flies by Saturn, and it sends back photos of something that just seems impossible. A giant, six-sided storm at the planet's North Pole, a hexagon. A year later, Voyager 2 flies by and confirms it. Back then, scientists kind of shrugged and figured, okay, it's a weird, temporary wave, it'll probably disappear. But then, fast forward a whole quarter of a century to 2006. The Cassini probe gets there and, yep, the hexagon was still there, just calmly spinning, waiting for us. And this is what makes it so mind-bending. In the universe, fluid dynamics, the physics of gas and liquid, love circles. Hurricanes on Earth, Jupiter's great red spot, they're all circular or oval. But this thing, it's a nearly perfect geometric shape with 6 straight sides. And it's been stable for decades, maybe centuries. Each one of its sides is wider than our entire planet. So, how in the world is this even possible? Well, the best idea we have right now is something called a Rossby wave instability. Basically, if you get the conditions just right, the right jet stream speed, the right rotation, you can create a standing wave pattern in the atmosphere. And that pattern can lock itself into a specific number of sides. For Saturn's North Pole, that number just happens to be 6. We've even been able to create similar patterns in rotating tanks of water in the lab, which is pretty cool. But here's the kicker. Even with a pretty solid theory, there's a huge question mark left. If the physics of Saturn's atmosphere creates this perfect hexagon at the North Pole, why isn't there one at the South Pole? The South Pole just has a normal, swirling, circular vortex. We don't have a good answer for that yet. The mystery continues. Okay, let's leave that beautiful mystery behind and move on to something a little more violent. Our next case file is a dynamical anomaly. We're talking about a planet caught in an actual death spiral. Just look at that number, negative 29.93 milliseconds per year. It sounds like nothing, right? It's the rate at which the orbit of a planet called WASP-12b is getting shorter every single year. The change is so tiny, it's like measuring the difference a single sheet of paper makes to the height of a 15-story building. But we can see it, it's real. And this is where it gets really profound. For decades, our theories predicted this should happen to planets that are super close to their stars. We called it orbital decay. But it was always a forecast, a simulation. WASP-12b is the first time we've ever measured it happening. This isn't a computer model. We are literally, directly watching a world die in real time as it spirals closer and closer to its star. So what does this actually mean? Well, for a long time, theory told us this whole process should be incredibly slow, happening over millions and millions of years. But seeing it happen this fast with WASP-12b forces us to go back and sharpen our models. It's a real-world stress test for our ideas about tidal forces, and it helps us understand how solar systems grow old and eventually fall apart. And the way it works is pretty wild. The planet is so close to its star that its gravity is literally pulling on the star's surface, creating these huge tidal bulges, just like our moon creates tides here on Earth. Those bulges on the star act like a brake, creating friction that just sucks the energy right out of the planet's orbit, causing it to spiral closer and closer. All right, so we've gone from a dying world to something else entirely, a system that feels almost designed. It's so perfect, it's weird. Welcome to our final case file, the TRAPPIST-1 system, an anomaly of pure architecture. Okay, get ready for this, because it is truly bizarre. The TRAPPIST-1 system has 7 planets, all about the size of Earth. But their orbits, they're locked together in this perfect gravitational rhythm. For every 8 times the inner planet goes around, the next one out goes around exactly 5 times. For every 5 of that one, the next one makes exactly 3, all the way out. It's a chain of perfect, simple ratios, a celestial music box. And just to give you some perspective on how nuts this is, let's compare it. The best we've got in our own solar system is a chain of 3 of Jupiter's moons. But TRAPPIST-1 has 7 planets, all locked in this delicate, intricate dance. We have never seen anything like it. So how on earth do you make a system like this? Well, the leading idea is that it didn't start out this way. The planets probably formed much farther away from their star. Then, over millions of years, they slowly drifted inward. As they got closer to each other, they gravitationally grabbed onto one another, falling into this resonant lockstep, one by one, like a train coupling its cars together. It's a beautiful theory for a beautifully ordered system. So, okay, we've seen a perfect hexagon, a planet falling into its sun, and this incredible clockwork solar system. These are all weird, persistent facts. But so what? What do they really mean for us? Well, this gets us to the true value of being wrong, and how these weird little anomalies are actually the things that push science forward. A great way to understand this is to look at a famous case that's already been solved. The Pioneer anomaly. For decades, the Pioneer 10 and 11 spacecraft seemed to be slowing down just a tiny bit more than they should. For a while, people thought, could this be new physics? It was exciting. But after years of digging, the real answer was found. It was just heat. Heat radiating unevenly off the back of the spacecraft was creating a tiny, tiny push. It wasn't new physics, it was just old physics we'd forgotten to account for. And that's how most anomalies end, not by breaking our theories, but by forcing us to make them better. Which brings us right back to the big question. What's the point of an anomaly? Why are these things so incredibly important to the whole process of science? And really, it all comes down to this idea. Anomalies, they exist in that tiny, razor-thin gap between our models being approximately right and being exactly right. And that gap, that's where all the good stuff is. That's where science lives. It's where we find new mechanisms, where we refine our theories, where we deepen our understanding of this incredible universe. These anomalies aren't failures, they're invitations. They're the very engine of discovery.